Hello guys, welcome back to my channel Algorithm Avenue. In our previous video, we have seen different techniques how not to initialize the weights and bias values. Now in this video, our aim is to discuss different techniques that are in practice to initialize the weights and bias values. Okay, now before diving into the video, let us see a quick recap of our previous video. Okay, this is a summary of our previous video. Okay, first we have initialized our weights and bias values to 0. Okay, we have initialized our weights and bias values to 0. When we initialize our weights and bias values to 0, we have seen that weights and bias are not being updated. Okay, second we have initialized non-zero constant. Okay, we have initialized weights and bias to some non-zero same constant values. Okay, same constant values. Now when we initialize weights and bias to some same constant values, we have seen that weights and bias are being equally updated. Okay, in each epoch our weights and bias are equally being updated. Okay, third we have randomly initialized smaller weight values. Okay, we have selected random values for our weights and bias values, but that random weight values are smaller numerical values. When the weights are smaller numerical values, we have observed that we face vanishing and exploding gradient problems. Okay, vanishing and exploding gradient problems. Okay, now fourth we have initialized random larger weight values. Okay, when we initialized our weights and bias to some random larger weight values, we have again faced the same problem of vanishing and exploding gradient problems. Okay, now these are the four techniques we have used in our previous video. Okay, now in this video we'll be discussing the techniques how to initialize the weight values. Okay, now when you keenly observe these 4 points, okay, you can eliminate this both. Okay, you can eliminate these 2 points. Okay, now when you keenly observe these 2 points, when we initialize smaller weight values, we have faced vanishing and exploding gradient problems, and when we initialize the weights to some larger value, we have faced vanishing and exploding gradient problems. Okay, now our aim is to choose a technique which is intermediate to both these techniques. Okay, which is intermediate to both these techniques means we need to choose weight values that are in between these. Okay, in between these two techniques. Okay, so that technique comes out to be Xavier or Glorot and He initialization techniques. Okay, these two are different weight initialization techniques. Okay, Xavier or Glorot. Okay, it can be called as Xavier or Glorot and He initialization techniques. Okay, these are different weight initialization techniques. Okay, now this Xavier or Glorot. Okay, this Xavier or Glorot is used for sigmoid or tanh activation function. Sigmoid or tanh. Okay, when you use sigmoid or tanh in the hidden layers, we use Xavier or Glorot. Okay, we use Xavier or Glorot weight initialization techniques. Okay, now when we use He initialization, okay, He initialization, we use it for ReLU activation function. Okay, when we use ReLU activation function in the hidden layers, we use He initialization technique. Okay, now in the Xavier or Glorot and He initialization technique, we have two variants. Okay, first is normal and second is uniform. Same in case of He. Normal and uniform. So we can say that we have entirely four different techniques. Okay, we have Xavier normal, Xavier uniform, we have He normal, He uniform. Okay, now this normal or uniform specifies that the distribution of the weights. Okay, distribution of the weights. Okay, now we randomly generate some values of the weights and bias values, right? Okay, we randomly generate some weights and bias values. Okay, now first we need to plot the distribution of randomly generated weights and bias values. Okay, if the distribution is normal, we need to choose Xavier normal or He normal. Okay, if the distribution of the randomly generated weight values is uniform distribution, then we need to use Xavier uniform or He uniform. Okay, this is what this normal or uniform specifies. Okay, now in the next section of the video we'll be discussing our first technique, that is Xavier normal. Okay, Now, before discussing different techniques to initialize the weight values, let us see a small intuition on why actually the formulas of weight initialization techniques are in this way. Okay, now let us take a sample neural network. Okay, let's say this is my sample neural network which contains 500 nodes in the first hidden layer and 500 nodes in the second hidden layer. Okay, now corresponding to this node, okay, I'm talking corresponding to this node. Okay, now corresponding to this node I will be having 500 connections, right? Okay, I'll be having 500 connections. Now when I calculate, okay, when I calculate z value, okay, I need to calculate z value for 500 connections. Okay, now z value is nothing but summation of I is equal to 1 to n xi wi. Okay, now let us say I'm assuming my weight, okay, I'm assuming my weights as some random values. Okay, my weights are some random values. Let's say they may be small, okay, some may be larger values. Okay, now z is equal to summation of I is equal to 1 to n xi wi. Okay, now where my xi is a fixed input and wi is some random value. Okay, wi is some random value. Okay, now, in this case, when I calculate, okay, when I calculate z value, I'll be getting some larger value. Okay, in this case, when I calculate z value, I'll be getting some larger value. Okay, why I'll be getting some larger value is I have 500 nodes in my previous layer. Okay, I have 500 nodes in my previous layer. Now, corresponding to this node, I'll be having 500 connections. Okay, I'll be having 500 connections. Means each connection represents, okay, each connection represents one xi wi. Okay, and my second connection represents xi wi, and my third connection represents xi wi. Okay, in this way, I'm adding 500 integer values. Okay, in this way, I'm adding 500 integer values. When I add 500 integer values, I'll be getting the final z value. Okay, I'll be getting the final z value as some larger numerical value. Okay, I'll be getting this final numerical value as some larger numerical value. Okay, now when my z value is larger, I'll be facing the problem of exploding gradient problem. Okay, when my z value is larger, I'll be facing the problem of exploding gradient problem. Now let us take the second case. Let's say this is my neural network. Okay, let's say this is my neural network. Now I'll be talking corresponding to this node. Okay, I'll be talking only corresponding to this node. Okay, now when I see this node, I only have two connections over here. Okay, so my z calculated z value is x1 w1 plus x2 w2. Same in this case also, I'm assuming some random w value. Okay, I'm assuming w as, okay, weight value as some random value. Okay, now when my weight value is some random value, I'll be getting, okay, I'll be getting this z value as some smaller value. Okay, as I'm adding only two quantities over here. Okay, you can see that I'm adding only two integer values over here, so I'll be getting some smaller value. Okay, so here in this case my z value is will be some larger value. In this case my z value will be some smaller value, so I'll be facing the problem of vanishing gradient problem. Okay, in this case when z value passes through the further layers, I'll be facing exploding gradient problem. In this phase, when my z value passes through the further layers, I'll be facing vanishing gradient problem. Okay, now let us take another assumption where I'll be taking n variable. Okay, I'll be taking n variable. Okay, now what actually this n represents is number of inputs to a node. Okay, this n represents number of inputs to a node. Now I'm taking this node. Okay, I'm taking this node. Now corresponding to this node, how many inputs I have? I have 500 inputs. So my n value will be 500. Now corresponding to this neural network, okay, now corresponding to this neural network, I'm taking this node. Now for this node, how many inputs I have? I have two inputs. So my n value will be 2. So now we can say that when my n value is larger, my z value is being larger. Okay, now in this case, when my n value is smaller, my final z value is smaller. Okay, when n value is larger, sorry, my z value is larger, and when my n value is smaller, my z value is smaller. Okay, now our aim is to make this relationship an indirect relationship. Okay, now when I increase the number of inputs, okay, now when I increase the number of inputs to a particular node, I'm getting z value as larger. But what is my aim? I need to reduce this z value. Okay, when my inputs are larger, okay, so sorry, when I have many number of inputs, okay, when my n value is larger, okay, I'll be having many number of inputs. Now when my inputs are larger, I need to reduce this z value. Okay, somehow I need to reduce this z value. Okay, in the similar way, when my inputs are smaller, my z value should not be much smaller. Okay, my z value should not be much smaller value. So I need to bring it to some range so that I'll be escaping this problem of vanishing gradient. Okay, so for this what we need to do is we need to multiply weights with 1 by root n. Okay, we need to multiply weights with 1 by root n. Okay, now corresponding to this node, I'll be having 500 weights. Okay, these 500 weights are some randomly generated weights. Okay, these 500 weights are some randomly generated weights. Now I need to multiply each weight with 1 by root n. Okay, I need to multiply each weight with 1 by root n. So I'll be getting weight values which are dependent on number of inputs. So in this case I have 500 inputs. Okay, corresponding to this node I'll be having 500 inputs. So this value will be 1 by root 500. Okay, now 1 by root 500 is some smaller value. Now when I multiply each input, okay, now I multiply each input with 1 by root 500, it will be some smaller value. So so when I take corresponding 500 smaller values, now this corresponding z value will be some medium value. Okay, it will be not much smaller value, but it will be some medium value. So I can escape this problem of exploding gradient. Okay, now in this case I'll be multiplying 1 by root 2. Okay, in this case I'll be multiplying 1 by root 2. So I'll be not getting much smaller weight value. Okay, sorry, I'll be not getting much smaller z value. So I'll be also escaping the problem of vanishing gradient. Okay, so the entire role is played by 1 by root n, where n is the number of inputs to a node. Okay, so from this we have the derived formulas of this 4 weight initialization techniques. Okay, so Xavier normal. Okay, Xavier normal is our first weight initialization technique. So the formula for this Xavier normal is under root 1 by fan in. Okay, this fan in is nothing but n. Okay, this fan in is nothing but n. Okay, where n is the number of inputs to the node and fan in is also number of inputs to a node. Okay, so this formula, okay, some in some implementations we use this formula, or we can also use this formula as well. Okay, that is under root 1 by fan in plus fan out. Okay, fan out represents number of outputs to a node. Okay, now I'm taking corresponding to this node, right? Now corresponding to this node, how many outputs I'll be having, that I need to place over here. Okay, that numerical value I need to place over here. This is Xavier normal initialization technique. Now when it comes to He normal initialization technique, it is under root 2 by fan in. Okay, under root 2 by fan in. Okay, now when it comes to Xavier uniform initialization technique, we initialize weights between these two limit values. Okay, now let's say limit value is 1, so I'll be getting -1 to 1. So I'll be taking random values. Okay, so I'll be taking random weight values only between -1 comma 1. Okay, I'll be only generating the weight values in between -1 comma +1. Okay, so this limit value can be calculated by under root 6 by fan in plus fan out. Okay, under root 6 by fan in plus fan out. Okay, now this is Xavier uniform. Now when it comes to He uniform, the similar limits, okay, we'll be taking the similar limits, but limit calculation is different. Okay, limit is equal to under root 6 by fan. Okay, these are all for weight initialization techniques. Now in the next section of the video, we'll be implementing all these 4 initialization techniques on a data set.
To make you understand the different weight initialization techniques much easier, I'm considering make circles dataset. Okay, in this video what we will be doing is we'll be training an model on make circles dataset. Okay, but this time the change we are doing is we are using different weight initialization techniques to initialize the weights in our model. Okay, first I am considering Xavier weight initialization technique. Okay, Xavier normal weight initialization technique. For that I am considering different libraries, and I am importing make circles dataset, and this is my make circles dataset, and I am splitting my data into training and testing, and after that I am converting from numpy to tensors. Okay, now this is my entire model. Okay, this is my entire model. The only change that I have made from the previous video to this video is I have imported an module, that is init module. Okay, this init module provides different weight initialization techniques. Okay, import torch.nn.init as init. This module provides different weight initialization techniques. Okay, and as I am using Xavier normal weight initialization technique, I need to use tanh activation function in the hidden layer. Okay, this is the second change. And the third change is I am initializing my weights to Xavier normal, and I am initializing my bias to 0. Okay, now what I am doing in this function is I am iterating through each layer, and I am picking up all the weights and bias values and initializing weights to Xavier normal and bias to 0. Okay, these are the three changes I have made from my previous video to this video. Okay, now I am considering loss function as BC with logit loss and optimizer as Adam optimizer, as this is my accuracy function, and these are my model results. Okay, my training accuracy is around 53% and test accuracy is around 48%. Okay, now you can see that at the 0th epoch I got around 50% training accuracy, and after 100 epochs training I got around 53% accuracy. Okay, now when you compare from our previous video to this video, in our previous video we have got around 50% accuracy. Okay, we have got exactly 50% accuracy, that is our model is predicting either 1 or 0. Okay, for my entire data set it is predicting 1 or it is predicting 0. Okay, but in this case our model is learning something and trying to predict the exact prediction for that. Okay, exact true prediction for that data. Okay, so that is why my accuracy scores are better than the previous video. Okay, but they are low because I have used a smaller model. So if I use some larger model I may get some better accuracy scores. Okay, next initialization technique is He normal initialization technique. Okay, the only change I'll be making is I'll be using ReLU activation function. Okay, as I'm using He normal initialization technique, I'll be using a ReLU activation function in the hidden layers, and I'll be initializing my weights and my weight values with He normal and bias values to 0. Okay, you can see that chiming normal. Okay, He normal is also referred as chiming normal. Okay, now this is my loss function optimizer, and this is my training loop and testing loop, and my training accuracy is around 51% and test accuracy is around 53%. Okay, now then I'll be moving to uniform weight initialization techniques. Okay, first is Xavier uniform initialization technique. Okay, now I'll be again changing the hidden layer activation function to tanh, and I'll be implementing Xavier uniform on all my weights, and I'll be turning my bias to 0, and these are my final model results. Okay, I got around 51% training accuracy and 47% test accuracy, and then I'll be moving to He uniform weight initialization technique. Okay, this is ReLU activation function. As I'm using He uniform weight initialization technique, I'll be using ReLU activation function in the hidden layers. Okay, and I'll be using chiming uniform weight initialization technique. Okay, He uniform is also referred as chiming uniform weight initialization technique. Okay, I'll be initializing my bias values to 0, and these are my final model results. I got around 50.12 training accuracy and 54.50 test accuracy. Okay, now the only change from my previous video to this video is my model is learning something. Okay, in our previous video our model didn't learn anything, but in this video, as we are using different weight initialization techniques, our model is trying to learn something. Okay, this is the entire video on different weight initialization techniques. Okay.